Awesome. Okay, so let me press go live and then we'll go live. Awesome. I think we are live. So welcome back, everyone. Thank you for joining us for today's Law Physics webinar. My name is Alejandro, and I'm going to be your host. Today, we are presenting data-driven exploration of cosmic mysteries using gravitational waves by Suvodip Mukherjee. Suvodip got his bachelor's from Ferguson's College, University of Pune, then his PhD at the Inter-University Center of Astronomy and Astrophysics in India as well, where he worked with Professor Suvodip. He then was a Grava Fellow at the University of Amsterdam, Lagrange Fellow at the Institut d'Astrophysique de Paris, and then a Flatiron Research Fellow at the CCA, at the Flatiron Institute. And then he moved to Canada to do another postdoc, to be a postdoctoral fellow at Perimeter Institute. He's now a reader or an assistant professor at the Tata Institute of Fundamental Research in Mumbai, India. And he's the principal investigator of the research group Data Theory Universe Lab. He works on data-driven astrophysics and cosmology using multi-frequency gravitational waves and electromagnetic waves to understand the history of the universe and its building blocks. We are delighted to have him in Law Physics today. So remember that you can ask questions over email, through our YouTube channel or Twitter, and then the questions will be read at the end of the talk. So without further ado, we'll turn it time to Suvodip. Thanks for joining us.
Thank you very much, Alejandro, and other organizers for inviting me for this talk and giving me an opportunity to present my work. I'll start sharing my screen now. And let me know if everything is working properly. Okay, can you please confirm that? Perfect, great. Okay, thank you so much for the very nice introduction. And that is it already said by Alejandro that I work on data-driven science or data theory cosmology. So that is basically the first part of the title of my talk, which says that I'm going to talk today about data-driven exploration of cosmic mysteries using gravitational waves. So when I say about I'm going to do a data-driven exploration, the first thing we would like to understand as far is what have we understood from the perspective of data about the cosmos so far. So this is a very nice image created by our colleagues in Carnegie and MPIA, which very nicely talks us about, in one side, how the observation has actually helped us in driving the theory of cosmology, in understanding its evolution. What we have learned so far is universe back at very early time was radiation dominated. Then at some point it became matter dominated. And now it's what we call as it's being dark energy dominated. And universe has gone through several phase transitions. So now universe is ionized. At some point it got re-ionized. And in the early high redshift universe was completely, everything was atom. And if you go to very high universe time, then again you go back to plasma. So this is the story which we have. Of course, our low redshift measurements are pretty good, which helped us in driving the cosmological model, which we call as the Lambda cold dark matter model. And what is important to understand is when it comes to really the understanding of the model, I say LCDM, we need still little understand about the model. We know it fits well, but it is still yet to explore several aspects of this model. I have only listed a very few questions over here, but no, it goes without saying that there are many more things which we do not know about the cosmos. I have just said here that we do not currently know what is the expansion rate of the universe, so-called the Hubble constant problem. What is cold dark matter? What is dark energy? Is it really the cosmological constant? Or is general theory of relativity the correct theory of gravity? And how do you have to understand that all these questions may not be there 50 years back? These questions actually came up with the help of our observations. And now there are several things we have not observed. We have not observed the very high redshift universe so far. We have measured something in the cosmic microwave background, which is really high redshift, around redshift of 1100. But something between, between that and redshift 1 or redshift 2, we do not have several observations so far. And what is really interesting that the era of astrophysics or cosmology is soon will be driven by observations. We have already several observations coming from the electromagnetic sector, because we have, with the help of several telescopes and several great scientists working day and night on these observations, we are able to map the sky from radio to gamma ray. And practically, this effort is kept on improving. This is one side of the story where we have very good EM observations to map the cosmos. Other side, we have basically opened up a completely new probe to the cosmos. We call it the beginning of the GW astronomy. Gravitational waves now is an observational probe, thanks to LIGO-Virgo-Kagala collaboration, and of course, several other ongoing efforts. So this is a slide which tries to explain this in the simple picture that when we talk about gravitational wave astronomy, it's not only about what LIGO-Virgo-Kagala have seen so far. It's much more than that. Similar to electromagnetic observations, you will expect gravitational wave also to be across a huge range of spectrum, something from 10⁻⁻15, -16 hertz to something, like thousands of hertz. And we have several ways to detect gravitational waves over this huge range of frequencies. The extremely low frequency gravitational waves, we expect to detect from the cosmic microwave background beam mode polarization, with the effort from several ongoing and upcoming detectors. In the around nanohertz range, we expect to see gravitational waves to be detected from radio observations of the pulsar timing array. In the millihertz range, we expect to detect gravitational wave from upcoming space-based detector called LISA. And in the extremely high-end gravity of this particular spectrum, above 10 hertz and so on, we are able to currently detect gravitational wave with the help of LIGO-Virgo-Kagala collaboration. In future, this effort will be joined by LIGO India, Cosmic Explorer, and Telescope. And as you can possibly understand, as like any other band observations, these different frequency bands will be actually covering very different kinds of physical phenomena, very different kinds of sources. If you explore you can go into explore very early universe scenario to the epoch when basically few compact objects like black holes or neutron stars or neutron star black holes are coalescing. So you are going to basically see a huge range of physics aspects happening over cosmic time with the help of gravitational wave multi-band observations. And in this sector, we are basically in the very dawn of the gravitational astronomy. We currently have about 88 to 90 sources we have detected so far with the help of LIGO-Virgo-Kagala collaboration, 01, 02, 03 combined. This is a very nice summary plot made by the collaboration, telling us about what kind of sources we have seen, what are the typical masses we have seen. I'll come to a lot of details over here on this. But this is our current state-of-the-art scenario with the help of gravitational waves observations. How this thing is going to change in the future? So if you ask me that question, I would say that the future looks pretty bright in the gravitational astronomy. So I'm showing you a plot in the left-hand side where you can see the typical range of masses we can probe using ground-based gravitational detectors. And that mass range is in the source frame is in the x-axis. And in the y-axis, you see the typical redshift range up to which we expect to detect the sources as an event, we could be confidently say it's a detection. So with advanced LIGO, we will be able to reach typically up to a redshift of 1 for a system of total mass around 100 solar mass. That's maybe a ballpark number to keep in mind. But in future, with Cosmic Explorer and Einstein Telescope, the next generation gravitational detectors, these are not yet funded, but these are very much in our proposal to get funding for that. That can actually detect gravitational wave way up to high redshift, up to redshift of 70 or 80. So now you remember what I was showing you in the very beginning of my talk, that our observations about the cosmos is currently limited up to low redshift. We have seen something up to very high redshift using cosmic microwave background, which is great. But now we have a very different kind of source present, which can see up to very high redshift using a completely different probe, which is complementary to electromagnetic observations. Okay, that's all about the high frequency gravitational waves. What about the in the millihertz range gravitational wave, which is detectable from sources like supermassive binary black holes or extreme mass resonance spirals? But in the through space-based detector called LISA, here is again a plot showing in the x-axis the masses of the binary systems, and the y-axis you see the redshift reach up to which we can detect the gravitational wave sources with a high signal to noise ratio, which are quoted in numbers over there. Again, the take-home message is very similar. With the help of LISA, we are going to explore the high redshift universe. And with sources, typically few thousands of solar mass to few 10⁷, 10⁸ solar masses. Keep in mind now, we are now going into an epoch of detecting cosmos using galaxies or quasars or cosmic microwave background, along with or supernova. Along with that, we are now entering into an epoch where I will be exploring gravitational wave sources across mass ranges to explore up to very high. Each of these mass ranges are kind of your different kind of sources, which helps you in understanding about the universe. And I really am quite fascinated to see when these both sectors, EM observations and gravitational observations, will be basically joining their hands together to tell us much more about than what we have learned so far. So now the question which keeps me awake in night is, how can you learn about the universe using these flows? What is the best way to combine sources? And what is the best way to understand new things which we have not explored so far? So in this paradigm of multi-messenger astrophysics and cosmology, there are two ways in which I find things fascinating. One is, how can we understand about the universe using these compact objects as a probe? That's the upper arrow in this particular slide. And the lower arrow, what you can learn is from our current understanding from electromagnetic observations, from radio to gamma ray, or stellar properties, what can you understand about the transient sources across cosmic history, going up to high redshift? And this paradigm, which I have tried to show by this simple diagram, is practically possible, because gravitational astronomy have some very salient feature. The way I would like to put it in one single slide, by trying to draw a 4-dimensional graph in a 2-dimensional plane. So please bear with me if there's some confusion in understanding that. What I find is amazing about gravitational astronomy is this 4 words, LRST, length, redshift, source, time scale. Gravitational astronomy is going to really be extremely great in exploring the cosmos because it has these explicit 4 ways to study the universe. When I say about length scale, you can see that we can study the universe from a few kilometer size when the black holes are coalescing to something like gigaparsec scale when they are propagating from a far away galaxy to us. So basically, from few kilometers to cosmological scale, we can probe physics using gravitational wave sources. In kiloparsec parsec scale, the physics driving the galaxy actually gets imprinted on black hole properties. I'll talk about it today's talk. About sources, as I already mentioned briefly, we have several kinds of sources, a species using which we can measure gravitational wave sources and up to high redshift, like binary neutron stars, BNS, NSBH, neutron star black holes, binary black holes, intermediate black hole masses, extreme mass resonance spirals, supermassive black holes. And these all sources are detectable up to quite high redshift. So that's an additional dimension which opens up. And one of the very important things is time. These are transients. and their time scale of variation, or the time scale over which you detect the sources, can be a few hundreds of milliseconds to seconds, hours, to up to a few years, depending upon the source you are measuring. So this extremely fascinating epoch when gravitational astronomy can help us in studying about the universe, and in my opinion, these four sectors is quite impressive for me for a single probe to basically explore, helping us in understanding quite a lot of physics. This slide tries to tell you kind of physics it can do, or more specifically, what kind of physics I explored using gravitational waves and other EM observations. So here, if I plot just one single plane from that previous slide of this 4D dimensional plane, I have just taken the redshift and the length scale problem now. So you can see, you can explore from black hole scale, like a few kilometer scales, to galactic scale, to cosmological scales using gravitational waves, up to high redshift, even if either using events, which you detect, or using stochastic gravitational wave background, which is not an individual detected. The range of physics which you can do, as I have already mentioned over here, in the cosmological scale, you can do expansion history of the universe, you can test GR in cosmological scales. You can search for exotic objects like primordial black holes using gravitational waves. You can learn about the galactic physics. You can learn about how black holes are forming in the universe. What are their redshift distributions? What physics goes in? You can learn about gravitational lensing of gravitational waves, which is we haven't detected so far as per our best understanding tells us, but sooner or later it will be happening. And finally, in the extremely small scales, we are able to try understanding completely unexplored physics, or sectors which have we expect signatures, but we do not have any measurements so far. And it goes without saying, I cannot do judgment in my single talk today. I tried to explain all these things. So I will now get to focus only just two topics in my today's talk. One is about what have we learned and what can we learn about the formation channels of compact objects across redshift using gravitational resources. And then I will tell you about something quite new we can explore in very small scales using gravitational resources in a completely new way, which is impossible before. So first part of my talk is going to be about the multi-messenger view on black hole populations. When I tell this, there are broadly two divisions you can think about: understanding black hole population from individually detected events, or also from the stochastic gravitational background. Again, one more narrow down on the research work. I'll be today talking only about events and not about the background. So when I tell about population of black holes or something, I want to understand the formation channels of black holes. One question to understand is, okay, what do we really measure from observations, or what do we really measure from observations so far as of now? One of the things which you can very neatly measure using gravitational wave strain data is its masses, or to be more specific, the redshift masses, which means the black hole's mass we see are actually 1 plus z times its true mass. So a black hole of whatever mass we talk about, let's say 10 solar mass, will appear 30 solar mass if you keep it at a redshift of 2. That's what it means. And another thing we can very nicely infer from gravitational wave observations is about the merger rate of black holes, or to be in general, merger rate of compact objects, which means you can ask how many sources of what masses are coalescing at what redshift or what distance. That's another quite interesting thing we can infer from gravitational wave observation. We can also understand about spin, which is also an extremely interesting topic. I'm not talking about it today in my talk because our current measurements of the spins are not great. It will be great soon. But by today's talk, I'm going to actually tell you about what can we learn from these two observations from our current data. So I'm primarily focusing on these two. So the question now is, well, whatever we have observed so far, around 90 binary sources, this is a simple, very nice cartoon diagram made by the LIGO-Virgo-Kagra collaboration, where it was trying to show what are the kind of sources we have detected across which mass ranges. That's in the y-axis. In blue are all the sources which you have seen LIGO-Virgo-Kagra. In orange, you are seeing the LIGO-Virgo-Kagra binary neutron star event classified on the basis of their masses. In red, you see the black holes which you have detected using electromagnetic observations. And in yellow, you can see the neutron stars detected the EM observations. So you can clearly see we have a huge population of black holes are detected thanks to the collaboration so far up to 10203 observation. So if I have to tell you a summary plot, what have we learned about black hole masses from this data? Let's ask this question. What we have learned so far is, well, for the very, very first time with the help of observation, we are able to plot the mass spectrum of compact objects. Let's talk about black holes here. And that's the plot which you are seeing. It's a phenomenological model. It's a power law plus Gaussian peak model. But what's really there in the data is we kind of see that, that the mass cross distribution is a power law. This is more black holes are present at the lighter end in comparison to the heavier end. And there seems to be a slightly overdensity in the number of black holes around 30-40 solar mass, which cannot be explained by simply a power. Remember, 5-10 years back, such a plot nobody would have imagined. Very first time we are telling you how binary black holes in the universe exist in which masses and how they evolve with this. That part I'm still about to come. So, well, that's one of the plot. You can ask, this is a phenomenological model. Did we try other models? Answer is yes. We have tried Gaussian peak model, broken power law models, several models we have tried. More or less, our understanding is very clear that, well, there seems to be a peak around 30-40 solar mass. After that, it falls down at higher end. And at the black hole mass distribution seems to follow a power law with a negative index, which means more sources at lighter end in comparison to the heavier. What about the merger rate? What have we learned about the merger rate of the compact objects from our current observation? We have seen so far that the merger rate is quite nicely can be explained by a power law form, 1 plus kappa. The value of kappa seems to be in agreement somewhere between 2 to 4. And those who are expert in the star formation rate history, they can quickly say that, well, from electromagnetic observations, we have seen that star formation rate in the universe typically follows something like 1 plus z to the power 2.7, called as a Maddow-Dickinson star formation rate. And when you plot that kind of line shown in the dashed over here in the left-hand side plot, you see there's a quiet agreement. And you would have expected that line because black holes are expected to form from the stars when you consider astrophysical origin of it, if you're not talking about primordial black holes. Great. So that's what we have learned so far from the observations using phenomenological model. But now we can ask a bit more deep question about where these binary black holes are coming from. What's the physics behind? Can we get some interesting physics out of it from these observations? So one of the things you need to understand that we, in the collaboration, the LIGO-Virgo-Kagra collaboration, with the help of gravitational waves, we do not detect a single black hole. We always detect a pair of black holes. That means you form a star into a black hole. That black hole needs to coalesce with another black hole form, and then it will merge. So there is a delay between the formation of stars and merger of black holes. So in simple way to understand that black hole mergers are going to be delayed. And this is a very nice cartoon diagram by Martina Chulinsky in her review article. But she was trying to show this basically this simple image diagram by this diagram that there is going to be a delay between the formation of stars and the mergers of black holes. Keep this in mind. Depending upon what formation channels we're talking about, we are going to have a very different kind of delay time distributions. Again, it goes without saying, we don't know much about this. So it is a completely going to be a data-driven sectors of using gravitational observations. Now the question is, what drives it? I mean, if I say you that there's going to be a delay in the formation of the black holes, in the formation of the mergers of the black holes with respect to the star formation rate, then you can ask, well, how the star formation rate evolves in the universe? And that's the plot you are seeing the left-hand side corner, which is coming from the Metalicity 2014 paper. With the help of infrared and UV observation, there's a constraint on the star formation rate in the universe, which peaks around redshift between 2 to 3. The low redshift end evolves with about 1 plus z to the power 2.7. So when you include this with the delay time, means the stars form, but they spend maybe hundreds of mega years to a few giga years to merge, then the corresponding merger rate of black holes can be obtained by basically doing an integration over the delay time and the star formation. And that's the plot you are seeing in the right hand side, showing you about the merger rate of black holes as a function of z. Key take home message from this plot is basically that, as you can see, when the delay time is more, let's say 2 giga years shown in red, that peaks at a lower redshift in comparison to the blue line, for which the delay time is less, like something like 0.5 giga years. That's because the black holes have spent more time in finding another black hole to merge in the red line. So they shifted to a lower redshift because of the look back time effect in comparison to the blue line. That's an observational effect that you can measure from data. And another thing we have learned from observation again is the metallicity of the universe. Remember, I am telling you about the astrophysical black holes. Astrophysical black holes form from stars. Stars have metals, or stars may be metal poor, depending upon when they are forming. So one of the key things which drives stellar properties of black holes are their metallicity. Black holes coming from metal poor stars are going to be heavier in comparison to black holes forming from metal rich stars. But then the question is, well, that's great, but how that controls the evolution of the black holes in the universe as a function of redshift? If you want to understand that, you have to understand how metallicity evolves in the universe. Here is again a plot from Metalicity 2014 review article, which is a data-driven measurement of the metallicity evolution in the universe with respect to the solar metallicity as a function of redshift in the x-axis. As you can see, the data claims to say that at high redshift, we have much less metals in comparison to the low redshift universe. Now, when you combine this effect with the delay time distribution, as I told you, it gives you some extremely interesting physical effect. I remember when you are observing black holes, you never know whether these black holes are coming from astrophysical origin or primordial origin. We know stars form from astrophysical objects. So if we really have to understand anything about primordial origin of the black holes, better we understand at first how the astrophysical black holes. There is no way out from that, because otherwise you can never understand how these black holes really the primordial one or the astrophysical. So coming back to the point of how this metallicity evolution is going to affect the black holes, the masses. So I already told you that black holes forming in low metallicity regions are going to be much bigger. That's typically because of the couple of physics. At first, the typical gene scale are much larger. So black holes, stars which form from metal poor regions are big, are heavy, and also when these stars form, they are very big. They can have pair instability supernova, and they can throw away a lot of material, by winds. Amount of material they throw away by winds depends on the metallicity. So, long story short, it implies stars forming at high redshift or in the metal poor region are going to have giving black holes which are bigger or heavier in comparison to black holes which are forming at a low redshift. Now think about a very simple picture which I'm trying to show over in this plot, that black holes which are forming at high redshift are going to be heavier in comparison to the black holes forming at the low redshift. But now I told you these black holes are not going to be merged right after they form, but they're going to merge after a delay time. Means the black holes you are seeing today must have formed from stars at a higher redshift. And this delay time is not a unique number. Not that it's a unique number, we don't know. No, it's a distribution function, because black holes of different formation channels have different properties are going to have very different delay time distribution. So we don't know the minimum time of the black holes to merge, and neither we know the distribution. So there's quite a few unknown things which are there, which it implies that when you see black holes at a lower redshift, these black holes are not going to come from a particular cosmic redshift at higher universe, but rather they're going to come from over a range of redshifts. If they come from a range of redshifts, you're going to mix black holes of different masses. It's an inevitable effect. You are going to mix black holes of different masses. That means when you observe using gravitational wave data black hole population, these black holes are observed at a particular redshift to merge, but they are not forming at a particular redshift from a star. They may be forming from a range of redshifts. What's the implication of that? The implication of that is the probability distribution of the black hole masses can get a redshift dependence. Depending upon at which redshifts they are merging and up to what's the typical delay time distributions of the black holes, they may be coming from stars which are formed at very high redshift when the universe was pretty much metal poor. Hence, the black holes can be heavier in comparison to the low redshift universe, but the metallicity in the universe is high, and you start seeing black holes which are lighter. This is a plot which is showing you that in the lower mass end, there is not much impact because of this pair instability supernova, but at the higher mass end, you are going to get a significantly different distribution, which is possible. So now the question is, this is the model I have told you, how this model fits the observation. What is our current data which we are looking at? So here is a plot on the black hole masses detected, means the redshifted masses in the y-axis as a function of the luminosity distance in the x-axis or redshift in the x-axis in the top. In the left-hand side, you are seeing the one mass companion masses, and on the right-hand side, you are seeing for the second one with the underlying assumption that M1 is always greater than M2. That's the construction. So that what you have seen, you can see in this data that we have, this is the black hole distributions we have seen, the posteriors. We have not seen very light black holes at very high redshift because the emission of gravitational wave signal from them is weak. We cannot detect them. We have not seen, so most of the black holes we have seen are typically in the low redshift range, but they extend quite up to higher masses. So can I explain this observation by the stellar physics we know, or do we really need any exotic stuff? So now I am showing you a plot where how the black hole population which you have seen from gravitational wave data using a physics-driven model, which I just now discussed with you using this mixing of black hole models to tell you how this black hole distribution looks. Of course, this plot looks extremely annoying to read because everything is so small and tiny. What the main take home I have to say from this plot is one needs to understand because of the several astrophysical aspects, there's a lot of degeneracies and correlations which one needs to explore from observations. So right now, as we often tell about our best fit cosmological model is a 6-parameter model. If I have to tell you that, what about my best fit gravitational population model? That's not going to be a 6. Just with the 6 parameters, rather we need maybe 12 to 13 parameters. So we need to really vary this in the setup of within a Bayesian framework. I'm going to show you a couple of summary plots which are obtained by basically marginalizing over a lot of astrophysical parameters. What have we seen so far? These black holes, I told you that we see a typical peak around 30-40 solar masses. What we have seen that these black holes can be explained by paired instability supernova coming from masses around 40 to 50 to 60 solar mass, as shown by the left-hand side top plot, which agrees with our current understanding of where typically the heavier the end of the black hole masses exists, the lower end of the black hole masses. We don't see any strong evidence of the redshift evolution. That's because of the only a few sources, but you can clearly see that from the right-hand side plot, there is a trend towards redshift evolution of the black hole masses. So heavier the black hole masses are as you go to higher redshift. And that is basically getting driven by the very fact that the metallicity in the high redshift is negative, is less. One thing I must point out to you that you can ask, is it an effect of prior? Are you assuming metallicity decreases? The answer is no. If you see this parameter over here, this alpha z right on the corner of this huge annoying corner plot, the last one, alpha z, that controls, and the gamma z, those controls the metallicity evolution. What you can see here, the gamma z parameter is extremely constrained to the negative range and is not a positive range. It's not positive means the metallicity evolution increasing with redshift has been completely ruled out by only gravitational observations, which agrees with the EM observations as well. And what's interesting, if you plot the merger rate of black holes as a function of masses and as a function of redshift now, you tend to see a mild evolution in its redshift, as you can see in the plot bottom. But I'm showing you the merger rates of black holes as a function of masses. In blue, you can see those black holes which are merging at a redshift of 0.2. And in green, you are seeing the plots for the black holes merged at a redshift of 0.8. What's the main take-home message you should understand from here? That we are seeing heavier black holes at a higher distance in comparison to black holes at the lower redshift. That's something we have seen in data, and that something is kind of agreed upon by this model and these constraints. And when you now can ask, well, now we have a physics-driven model, we can some constraints on the delay time distributions of the black hole. Here is a plot on the delay time distributions of the black hole from gravitational wave data GWTC3 for different kinds of population assumptions. As you can see right now, the constraints are quite weak. But one thing is interesting that for priors above 2.5 or 3 gigayears seems to be strongly constrained for the orange curve, but for the green one and the blue one, there seems to be quite a support. That what it means that black holes can come from very, very high redshift and can coalesce today. Another way to understand what I'm exactly saying now is basically the black holes you are seeing today to merge in the LIGO-Virgo-Cabrera observation band may be coming from high redshift. That means this is a completely new probe to study the high redshift universe. Remember, the stellar properties of black holes or stellar properties at high redshift is not well measured from observations so far. So gravitational wave is actually opening a completely new window to learn about the stellar physics happening at very high redshift by studying the dead, basically studying the black holes, which are the end product of the stars. And the right-hand side of the plot, you are seeing a plot from the merger rate constraints from the gravitational wave observations. Again, it agrees pretty well with the GW263 observations from LIGO, showing you that typically it's driven by the star formation rate, which and that peaks around a shift between 1 to 2. And one of the quite interesting events which you have detected in gravitational wave is one of the very heavy mass black hole. It's maybe known to many of you, called as the GW190521, a heavy mass binary black hole around 860 solar mass. Soon after this came up, people started talking about maybe this is a source which is unlikely to origin from a astrophysical source, because you don't expect such high masses. What we have seen by basically this physics-driven model, because your metallicity in the universe evolves as a function of redshift, black holes of these heavy masses can form at high redshift when the metallicity of the universe is low. So if these black holes are forming from stars which are extremely metal poor, you expect for them to even merge at a lower redshift because of the delay times. Or in other words, GW190521 is not an outlier according to a physics-driven model which I am presenting over here. To summarize, not my talk, but just this part of the slides of the work, what I told you is that pale-symmetric supernova mass scale agrees with the theoretical range from gravitational wave observation. Model naturally predicts heavy mass black holes, binary black holes, detectable at low redshift, like 190521. Constraints on the delay time distributions one can obtain by this model. And what is very, very interesting, that a concurrent picture of the metallicity or the star formation rate evolution of the universe and the black hole distribution now seems to be in agreement, which is a very, very cool thing, because now that means we can learn about high redshift universe using the black holes which are merging and observing now using current gravitation. Well, that's the part of the talk I presented. Now you can ask what more we can do in the frontier of gravitational wave population. I told you I can use metallicity to understand about black hole masses and their metallicity evolution, delay time to understand, their population, how they evolve. Now the natural question to ask, because I started telling you about multi-messenger from the very beginning of my talk, how the multi-messenger part actually plays a role. What's interesting is black hole properties of the universe can actually tell us about the chemical composition of the universe. And that's basically because black holes are forming from stars of what kind, that depends on the metallicity evolution. How many black holes are merging, they're going to depend on the star formation. And metallicity in the evolution in the universe is not only traced by gravitational waves, but also by other sources like emission lines. You can see emission lines of oxygen, hydrogen, nitrogen, carbon. And you can see emission line galaxies. You can see line intensity mapping of different emission lines from electromagnetic observation. Here is a very nice snapshot from a simulation made by Phil, where they showed that from a cosmological simulations, where you expect to see emission lines. In blue, you see extremely bright galaxies. We call it emission line galaxies, ELGs. And those which are not detected, a diffuse background, you can also see like a line intensity mapping observations in future. And just from the very fact that metal lines can be detected using emission line galaxies or line intensity mapping, this same metal lines is going to control the stellar properties and hence the black hole properties. As a result, there's going to be a direct one-to-one correlation between the observed black hole mass redshift distribution and the emission and galaxy properties in the universe. A completely new way to study the chemistry evolution of the universe, chemical evolution of the universe using multi-messenger observations. And here I'm showing you a plot on how this can play a very interesting role. This is a very messy plot, so try it. So bear with me. In different colors, you are seeing the redshift evolution. From blue to red, you go from redshift of 0 to 2.5. In the x-axis, you are seeing the number of gravitational sources you expect to detect. And the y-axis, you are seeing the typical number of emission line galaxies you will measure. Now, the very fact that that metallicity evolves in the universe as a function of redshift, and black hole distribution is going to follow the metallicity evolution, you will expect a very, very interesting correlation between the emission line galaxies properties and the gravitational wave merger. Here I am showing you a plot for large delay time, means black holes are taking more time to merge by large marker size, and small delay time means black holes are merging sooner by the small mergers, small marker size for different emission lines, say O2, O3, and H alpha. What is quite interesting now that vary from this very fact that both are driven by the same physics, you will expect a correlation in these two sectors, and one can measure this from observation. That means now from a crude population model of understanding the black hole properties, I can go and tell you about the black hole properties and about the chemical evolution of the universe by combining emission line galaxies with black holes, which are detectable from upcoming detectors such as Sphere X, DAISY, in combination with LIGO, Virgo, Karma. So this is a paper which I have written with my collaborator Azadeh Digza. It's now published in Abj Letter, where we have shown that how the formation channels of black hole, mainly the delay time distribution, can be constrained from this very new correlation which I pointed out in this paper, using LIGO, Virgo, Cabra and the line density mapping signals from Sphere X and combining the emission line galaxies from DAISY. And you can clearly see that from a measurement which is currently extremely poor, we are going to make a 10 to 20% measurement of the delay time distribution and the typical probability distribution of its delay time from these observations. So, which I find quite fascinating now, because we are going to explore extremely high redshift universe in the galactic scale using black holes. Remember my very initial plot, black holes gives us gravitational waves can teach us about a quite large redshift and about a different length scale. So far I just talked with you about length scale we can explore using gravitational wave in the galactic scale, driven by metallicity evolution, star formation rate, and so on. Other thing which I promised to talk today about is about the extremely small scale physics we can learn from gravitational wave observations, or basically things we don't know about so far, because who has gone and measured black holes when they are very few kilometers? So here comes a way to actually try to understand about the unexplored physics using gravitational wave observation and search for deviations from fiducial model or your favorite model. So here I'm trying to show you, let's say it's the binary black holes coalescing. In the left-hand side, you are seeing a gravitational wave strain, your best fit model, hidden something in the noise. So this is an image created, made by a PhD student from Peribel Institute, Guillaume Dedron. Let's say this is your actual model you are considering, but that's not the true model. Your actual model is something quite different, shown by the green line in the right-hand side. And there is a deviation. You don't know about the green one, you possibly just know about the red. How do you going to measure the actual physical effect? Now you can ask the question, what all can drive this? Well, there are many things. Unmodeled GR effects, GR may not be the true theory of gravity, unmodeled cosmological effects. And when gravitational wave propagates through space-time, there can be effects from cosmological origin, which can be lensing, which can be gravitational wave propagation effects, which can distort gravitational waves. There can be completely unmodeled, unknown astrophysics, which we do not know about. And there can be unmodeled known astrophysics, like black holes may be in a disk, maybe around a black hole in a thick disk where it is getting a bit delayed because of friction, downward friction and so on. And remember, one more thing is very, very crucial. You cannot forget about unknown detector noise properties. Everything plays a role when you really want to get into a neat measurement for the first time, because you really don't know what is signal and what is noise. Well, these are my interesting physics effects which can happen, I told you. Question is, how can I explore this unmodeled physics from data? What we have proposed that, well, there are maybe a couple of things which, as a physics-driven way, again, same physics-driven hammer comes here, which can help you in exploring even the unmodeled physics. What are those? If there is a common effect, which is the green line in comparison to the red line, means you have a residual which is of astrophysical origin, not coming from your detector. It is going to be common in multiple detectors. That's a key feature. Number two, a deviation which you are seeing in the gravitational waveform can be modeled as a loss or gain in the energy from the fiducial model. And third, these deviations are likely to depend on the gravitational wave source properties, such as its mass, such as its spin, and so on. So this, in our opinion, me and our collaborator, as I come over here, Guillaume Dedron, myself, and Louis Lena, what we have proposed is a completely new technique called SCO, structured correlated residual, to look for these particular effects from observation by basically hammering on these three physical effects. So first point, physical effects will be common in multiple detectors. So what we propose to do is what you have residual between the gravitational wave best fit model and your data, and you can do a cross correlation between the detectors, the residual signal, to find what is common. Second step is about a physics-driven way to understand, is there any coherent deviation from your model? Remember, one of the key challenges is to distinguish between what is a physical effect and what is coming from noise. So the first one, cross correlation, helps you beating a bit of those uncorrelated noise. That's great, but that's not sufficient if you really are driven by very tiny, minute deviation. Remember, when you are going to look for any new physics, it's not going to be showing up right bump as a high signal on your data. And there is a lot of reason behind that. It's just not because we don't know the physics we are going on, but also because of the degeneracy between the source parameter and the physics you are modeling. It is possible that your new physics you are trying to measure mimics some other source parameters of general theory of relativity. As a result, any tiny deviations needs to be very minutely measured from observation. So a physics-driven model or template to search from the data will be really nice and cool. That's the second step. And the third step is basically projecting the correlated signal on this template, which now as the source depending upon the gravitational wave source, such as its mass, such as its spin, rather than just naively combining. And these are the three salient features of our method SCORE. So let's take an example how SCORE is going to perform. On the right-hand side, you are seeing a standard best fit model in blue and some beyond model signatures, doesn't matter what right now, in green in the right-hand side. So let's say that this is I have generated the data. This work has been led by Guillaume Vidron. So we have obtained, let's say, a mock data of gravitational wave signal. The residual signal in two different detectors having uncorrelated noise. That's the one which you are seeing on the left-hand side and the right-hand side top left. Well, now you do a cross-correlate these two residuals between the two detectors. The green line is your beyond model signature. You can clearly see the correlated residual is way low. Even after you have correlated, you remember you still have so much noise uncertainties. You still have deviations. It's not so easy. Then what do? You take an agonistic approach on the template you choose to project this cross-correlated signal on this template. And when you combine in a physics-driven way several sources, so in this particular plot, it's obtained from around 500 gravitational wave sources, you start seeing that you try to get infer the injected deviation in that green line quite nicely in the left-hand side plot. The alpha 1 is the strain or the strength of the deviation from the best fit model. What's interesting to understand that, well, you are talking me about template. How will I know the template? I don't know the model. I don't know the physics going on. I may be using the template. And here comes a very, very important aspect of the method score. Score can search for both model dependent and model independent deviations from your fiducial model. A way to project this in a simple way is basically, let's say that you have taken a beyond standard model signature on the black hole binaries or compact object binaries for individual masses of 1 solar mass, 2 solar mass, and 5 solar mass. The blue one, you are seeing the true deviation residual power. I have not told this at all, the technique, that there is a deviation of that kind. The very fact that I model the deviation in terms of the source parameter, I vary source parameter and I model the template. You can start seeing that depending upon the source parameter, how the blue line changes, the green line kind of tracks that. Of course, it will not track it perfectly. It cannot track it perfectly because it's not a stitching of one model assuming the another model. No, it's a completely data-driven hammer. So there is a noise, there's an uncertainty. But what is cool thing to understand that it is tracking the light regime. So when you combine several sources, we can get to basically measure tiny deflections or distortions if exist in gravitational wave data. And these are very difficult to explore and currently are not explored at this full glory using a method as available like SCORE. And there are ongoing efforts by us on this front. So all I'd like to say that a new way to explore unmodeled physics. So everybody who loves to unmodel physics, whether it is dark matter signatures on gravitational waves, lensing, beyond GR effects of accretion disk, effects of waveform systematics, come up with whatever you feel like an artifact or unmodeled scenarios. SCORE is great in exploring those sectors. Certainly, SCORE is a very new frontier, so it has several. It will also have multiple shortcomings or challenges to overcome. This is a very bleeding edge of technology which I'm talking about. So more work needs to be done on this front. And with this, I will like to conclude my talk telling you about, well, data-driven exploration of gravitational waves seems to be a really new frontier. We are not only going to learn about the physics or astrophysical phenomenon we have learned so far from EM observation. Rather, we're going to learn about something very new from this sector. With the help of multi-band observations, we can do inference data analysis with robust statistical techniques to tell us about astrophysics, cosmology, and the fundamental physics going on. And using favorite models or using our best understanding so far, we can make predictions which can be tested from our current observations. So it's really a circle of inference and predictions which goes together in this sector of data-driven exploration using gravitation. And it is really possible because of multiple detectors ongoing or upcoming. I've given a timeline over here. LIGO, 2 detectors, and Virgo is currently operational. O4 will be starting in the coming next year with Kagra. LIGO India is currently approved, which is most likely going to happen by sometime at the end of this decade, if not later. LISA is funded and going to be likely to be operational from 2035, 2036 onwards for about 4 years or so. And in future, proposals are currently ongoing to have measurements from Cosmic Explorer and Einstein Telescope in 2040 onwards. So I would like to conclude with a couple of summary points that I mentioned today in my talk. The gravitational sources can tell us about the hierarchy of the universe. This is something, the take-home message which you should remember. It's not in future, but now, by very much from the population of sources we have measured. Binary black holes mass distribution can tell us about its formation channels. Soon, we are going to show you plots with the help of LVK observations, how black holes evolves as a function of masses and redshift. And such a plot will really tell us not only about astrophysics, but also about if black holes of non-astrophysical origin exist in the universe or not. That's key because primordial black holes are still hypothetical objects. To understand discover them, you need to first understand how astrophysical black holes exist. Synergy between the emission line galaxies, ELGs, and line intensity mapping with the gravitational observations can tell us about the delay time distribution and is dependent on the chemical composition of the universe. And finally, in the extremely small scale physics or something which is happening at the near to binary compact objects, we have proposed a new way called SCO, structured correlated residual, which can search for unmodeled physics from gravitational observations, basically using it. With this, I will end my talk and will be happy to take any questions. Thank you very much.
Awesome. Thank you, Suvodip, for this comprehensive and nice talk. I see we are a little bit past the hour. Let me check the...
Sorry about that.
No worries. So let me see if there are questions over YouTube. I received a question. Let me see this one. Let me start with one by myself. This is if you go back to the mass distribution of the binary black holes, is there a physical explanation? I don't know if you said it about it. Why do we have like these 2 peaks? Is there a way to nicely understand it?
Yeah, got it. That's a very good point. So see, try to understand this way. Suppose you have black holes coming from the stellar population. First question to ask, how the stellar mass are distributed? We have not seen stars at the very high masses so far. It's very poorly measured. At the lower end, you still have measurements. Seems to say that there is a power distribution called, one of the favorite models is for the Krupa mass function, which tells the black holes follow something like, like a power law form. On top of that, now if black holes are forming from stars and extremely big stars throw away all this material by pierced instability supernova, they will not form black holes at the extremely high end from those stars. That means you are now going to form black holes from very high masses to up to a mass which is limited by the paired instability supernova. Paired instability supernova mass is metallicity dependent. This is a key point to remember. So now, if you have a power distribution and you start piling up a lot of black holes around the mass, Because black holes don't form at higher end easily, you are going to form another peak. And that's our explanation for the second peak, which you're seeing in the black hole distribution between 30 and 40 solar mass. You can go and ask this question, why is it, is it at 30 or is it at 50? Why is the range? Because these black holes are coming from stars whose metallicity are not fixed. Stars comes, of course, different metallicities in cosmic time, depending on the galaxy properties. So this peak is going to be slightly smeared along this true value. And possibly there's a hint towards that from our current observations. But for sure, in future with O4, this understanding will be improving, or we can even rule out such models. So yeah.
Awesome, thank you. Okay, receive this question. It says, even if we do not have data on the spin, can this mixing of black holes that you're talking about tell us something about the spin?
Yep, that's right. Yes, sure. Depending upon the formation challenge of the black holes, you can also start predicting about the spin distributions. You can say that, okay, well, these black holes are coming from hierarchical mergers or not, or the isolated binaries. Those are going to have a very different spin distribution. In this work, we have not included that at all. And one of my PhD students is currently working on that project. But what is the simple answer, way I can answer that question right now? That answer is yes. As soon as we have a posterior distributions on the spin distribution and its rest-state evolution, if you see, we can actually start putting, some constraints on these kind of models. I must say here one thing, that recently with again with Christos Karanthanasis, we have put out a paper called GWSIM, which is a population synthesis model for basically also incorporating the spin distribution. It's an open source code to basically generate black hole populations, including spin, including mass distributions for different cosmological models. So if you want to ask this question yourself, just go and play with it.
Okay, let's see if that one has a follow-up question. Sure. And I think, Roberto, you have a question?
Yes, I have a question for Suvodip. I was wondering, because with all these analysis, for more or less I understood, you use the Bayesian analysis, right?
Yep.
So is there any space for training or to use machine learning techniques to explore the data-driven part of the
yeah, totally.
analysis?
I mean, totally. Machine learning is one of the important things when you have a lot of data and you can train it well. So yes, the answer to your question is yes. We are one of the key challenges in such problems, as you have exactly said, Bayesian methods, they are costly. And one of the approaches in future will be basically putting this towards machine learning by basically helping it to learn how to predict the posterior from observations. And if we can get something faster in comparison to what we are doing now. But there is as usual to all of the machine learning problems, I must say, it all depends upon how well I can train my data set. If you're really going for new physics and you're paying billions of dollars for measuring something new, you may not be very sure to just discover what you have trained on. So even if I want to measure something with a Bayesian, with a machine learning technique for getting it faster, I will still rerun it on a Bayesian and a technique to find something. Is there any mismatch from the machine learning? If not, then that's great. But if yes, that's needs more script. So I will keep on continuing both sides.
Okay, thank you.
Yeah.
Great. I don't see more questions here. Then I might ask perhaps the final one. So at some point for the last part of your talk, I missed something a little bit. So you said you can use a score to model and physics, like when we don't know the physics of the model, perhaps. But I think you also mentioned you can search with your method for physical mechanism. Could you please explain that?
That's right. Yeah,
I missed that part.
But that's great. This is a good thing because I can explain something more on score. So I made a statement. Let me rephrase the question. I said a statement. I can also explore physical effects using this unmodeled search technique scope. How is it possible? Is basically from this step where you project it on a template. That means, suppose you have a gravitational data. You take your favorite model, okay? You take your favorite blind black hole model for which it has a maximum support from the posterior using maximum likelihood estimate and so on. Now you have a residual on the data. You are now asking, is your favorite model, whatever it is, let's take me my favorite model. I want to search for deviations from GR by some effective field theory approach. I want to understand, is it exists in the data or not? If I'm a theoretician, I possibly know how the signal look. I can go make a template for that particular signal, project it on the cross-correlation signal, and ask, is there a support for that from the data? What it means is that you can basically use this technique to search for a very specific models, as well as if you don't know, but you have a physics-driven approach. Let's say gravitational energy, any deviation from general relativity can be modeled as an energy law, more energy loss or gain in comparison to what GR will predict. That's a very, go ahead.
Yeah, so sorry. But what if I start from this EFT theory and do the game from the beginning? So what you're saying is that perhaps that, I don't know, like that higher power at a particular location or whatever is going to disappear if you got that model, right? Like if you are modeling.
That's right. Yeah, that's right. So what it means that suppose you have a residual, okay? Your residual says that there's slightly more residual in certain frequency bands in comparison to the GR wave.
Yeah. Okay. Perhaps what I'm missing is why is this different from starting from, let's say, okay, my favorite theory is the theory of Suvodip, and then do this analysis as opposed to.
Okay, got it. That is because there are plenty of theories, and it is very, very difficult to search for, make waveforms and make a parameter estimation for all different waveforms, occupying a huge theory space and parameter space. Think about the problem, like you have 15 parameters. You are going to explore the gravitational source properties, and you have maybe 10 theories. Is going to be a huge, large amount of effort. I mean, you may not reject anything.
Yeah.
So score you need, because your GR is great. It has a nice prediction. Unfortunately, there is no next theory which is so popular so far. That means you need a technique which is fast. You can combine hundreds of black holes. There are many cycles over a large frequency range to quickly tell you, do I see something interesting? If so, go behind it. That's what SCORE gives you. Okay.
Awesome. Okay. Thank you very much. Let me see. I don't see more questions, so people can go to your webpage and look for your email or ways to contact you. And I believe, right, Roberto, this is the last webinar of this year. We will recombine in late January, I think, early February. We have to check. Stay tuned. Awesome. So thank you very much for the Suvodip.
Thank you very much for attention, and thank you for inviting me.
Thank you everyone for attending to this talk. Okay, see you soon.
Bye.
Okay. Oh, he left.